For this second atmosphere lecture, we're going to talk about radiation, which I was referring to in the last set of slides. So we'll talk about what solar radiation is. We'll talk about something called albedo. We'll talk about humidity, the dew point, and then and then we'll finish up with one more small section about what happens to air when you heat it and cool it. So what did I mean by solar radiation when I was talking about the layers of the atmosphere and how they can block certain types of solar radiation? So the sun is the source of energy for life, and every day the sun is basically emitting what we call solar radiation, and that solar radiation travels to Earth and then bombards Earth's atmosphere every single second of every day. So just to kind of give you an animation of it, again, is this graphic playing through here. Or if you think about the sun, there is energy that's coming off the sun that travels towards Earth every minute of every day and bombards our atmosphere. When we're talking about the sun's radiation, what I mean more specifically is electromagnetic radiation. So you may have seen this before, but basically this is like all the different types of radiation that we can have. And it's arranged by their wavelength. So shorter wavelength radiation is like gamma rays is the smallest, which just means that they're very close together. And then you have X-rays, you have ultraviolet or UV light. Then we also have visible light. Then we have infrared light, microwaves, and radio waves. So all of these waves are emitted by the sun. All of these types of energy are emitted by the sun. But our atmosphere does a pretty good job at blocking gamma, X-rays, and some of the ultraviolet light. It doesn't do a good job at blocking the other types of light like visible light, infrared, microwaves, and radio waves. So of the radiation that does reach the surface, about 8% of the 100% of ultraviolet light that hits Earth does go through the ozone layer, does come to Earth's surface, which is why we get sunburns and skin cancer. So on Earth's surface, we do have ultraviolet light. We have visible light. That's the reason that you see color is because solar radiation reaches Earth's surface and visible light reaches Earth's surface. That's why we see color. We can also have infrared radiation on the surface as well. So if you had an infrared camera, you could point that around and you can see infrared light using the infrared camera. So of the radiation that does reach the surface, it will take one of three paths. So it's either absorbed at the surface, and about half of the radiation that reaches Earth's surface is absorbed. And when it's absorbed, basically it heats something up. So if you absorb heat and you take in heat, your temperature raises or rises. I don't teach English. I don't know what the correct word is there. Anyway, the temperature increases because you're absorbing heat. That's about half of the radiation that reaches our surface will do that. Another part of it gets absorbed by clouds in the atmosphere. Then the other two options that it can take is that it could be scattered. So it reaches Earth and then it just kind of scatters in all directions, or it's reflected back up into the atmosphere off of certain types of surfaces. So solar radiation that reaches the surface either gets absorbed, scattered, or reflected. That's the three options. So if you look at the reflection, we can characterize reflection by something called albedo. So albedo, just to give it a definition, tells you how reflective something is. So if something is usually lighter in color or shiny, it's going to be reflective, and it has what we call a high albedo. On the other hand, if something has a low albedo, it's not reflective at all. So it tends to absorb heat, and it might be dark in color. So as an example, snow has a 90% albedo. So what that means is that 100% of the light that reaches Earth's surface, if it hits snow, 90% of that radiation or that light goes back up, reflected into the atmosphere. If you have something like asphalt or a road, 100% of the light that hits that asphalt or hits the radiation that hits that asphalt, of 100% of it, it's going to absorb 90% and only 10% will reflect back up into the atmosphere. So it's got a low albedo because it does not reflect light. So when radiation is absorbed, if you have radiation like ultraviolet light that hits your skin is going to burn. You're going to get a sunburn and your skin is going to feel hot. It's because you've absorbed radiation. So when things absorb radiation, they heat up. So radiation is converted to heat when it's absorbed, And just to kind of recap what I talked about before, the thermosphere, the outermost layer of the atmosphere that's on the border with outer space, absorbs X-rays and gamma rays. And then the stratosphere, with the ozone layer, that absorbs ultraviolet radiation. So those heat up because they absorb that radiation. So absorbing radiation is a good thing to an extent. So the greenhouse effect basically is the result of the ability of Earth to absorb radiation and to heat up. So as the sun's radiation travels to Earth and travels through our atmosphere, if we have dark surfaces on Earth, that absorbs heat and it makes Earth's surface more amenable to life. There's also greenhouse gases, so there are gases in the atmosphere that help to trap Earth as well, which we'll elaborate on in a couple slides from now, or a couple lectures from now, that also help to heat up Earth. So the greenhouse effect is a good thing because it gives Earth the ability to heat up a little bit due to absorption of radiation. All right, so I got 4 thinking questions here for you. They're multiple choice questions on atmosphere quiz 2. So first, if Earth's atmosphere contained more black soot, would global temperatures increase or decrease, and why? The second question, if Earth's atmosphere was thicker, would global temperatures increase or decrease, and why? If there was no ice on Earth, would global temperatures increase or decrease? Excuse me, and why? And if trees and all vegetation were white instead of green, would global temperatures increase or decrease, and why? So as always, feel free to pause, come back when you're ready to move on. All right, what I want to point out is that if we're talking about the atmosphere, water tends to stay in the atmosphere for about 11 days. So if you get a drop of water that evaporates from either a pond or a lake or the ocean, it will stay in the atmosphere for about 11 days on average before it rains back down as precipitation. So if we're thinking about water in the atmosphere, I just want to recap the properties of water. So you've probably learned this at some point, but water is the only substance that exists in all 3 states, frozen, liquid, gas, or vapor on Earth's surface. And the ability of water to change from one phase to the other is what drives a lot of our processes that we have on Earth in terms of the hydrologic cycle, in terms of weather, in terms of climate, in terms of life, creating life in the first place. But what I want to point out is that it's kind of hard for water to change state or to change phase from like a solid to a gas or a liquid to a solid to liquid, vice versa. And we can refer to that as something called latent heat. So if water is trying to change from a frozen or trying to melt, if water's not trying to melt, if water is melting from going from I'm really not doing well at this description right now. If water is going from frozen to liquid, it takes a lot of heat and it's got to absorb a lot of heat before it can change phase. So it takes a lot of heat to kind of break apart these ice crystal bonds and separate them to create liquid water. So what I'm getting at though is that it takes a lot of heat for water to change phase or state. But if temperature is raised, then water is absorbing heat. And if temperature is lowering, then you know that water is releasing heat and heat is lost. So now that we understand the properties of water and we've kind of gone back over the idea that it takes a lot of energy to change the phase of water or the state of water, let's talk about water in the atmosphere. So there's a couple definitions that we'll go over. The first is humidity. So we all know what it's like to have a hot, humid day. So humidity basically is an estimate or a measure of the percent of moisture in the air. So if you have a really high humidity, then you're going to have a much higher percent of water that's just sitting in the air, in the water vapor surrounding. So tropical rainforest, for example, could be foggy because it has a lot of moisture, a lot of humidity in the air. So that's humidity. That's measured as a percent. We also have the dew point. So the dew point is a temperature that the air has to be for it to be saturated. So for example, just the best way to show this is with kind of this analogy here. So we have the atmosphere. The air temperature is 53. Let's say the dew point temperature is 51. Let's say the air temperature goes down to 52 and the dew point is still 51. As soon as the temperature of the air is 51 and that equals the dew point, which is also 51 degrees, what will happen is that this is the point at which moisture can form. So you will get fog, you will get clouds, you will get rain. when the dew point equals the temperature of the actual air in the atmosphere. If the dew point and the temperature aren't the same, you won't get fog, you won't get condensation, you won't get rain. They have to be equal. So if you want to know if it's going to be super gross outside on a hot summer day, you can use the dew point in terms of trying to understand what dew point would mean in terms of what it feels like outside. So if the dew point is between 50 and 60 degrees Fahrenheit, then it'll feel awesome outside. But if it's above 70 degrees Fahrenheit or more, I like this little emojification of it, it's going to feel downright gross. So the higher the dew point, the more moisture in the atmosphere, the more gross it feels outside and the more sticky and humid it will be. When we're talking about water in the atmosphere, we need to just recap the definition of condensation. So condensation is taking a vapor and turning it into a liquid. So air, water, vapor, turning that into a liquid. That's condensation. So condensation is going to occur when air is saturated with water vapor. So when it's typically kind of close to the dew point, or if you have a very high humidity percent on a given day. Just to give you an analogy or an example of this, so let's say, again, the lemonade temperature, you got a lemonade temperature here, and then it's at air temperature. So if the lemonade temperature equals the air temperature, you don't get any condensation on your glass. If you add ice and you lower the temperature, what is going to happen is that you're going to form moisture on the outside of the container because you have now lowered the temperature and then you have met the dew point at which condensation will start to form. All right, so question 5 on your quiz. So which of the following best corresponds to the relationship between dew point and condensation? So to finish up here, we have just one more small section that's talking about air pressure, condensation, and precipitation. So let's talk about air pressure and density. We can measure the pressure of the air. If you are sitting at home right now, you're probably feeling 1,000 millibars of pressure on your body, but you're used to it because you have evolved and adapted to live at Earth's surface where we have a high pressure of air pressure on the surface. So if we're looking at atmospheric pressure, we have pressure here in a unit called millibars. Close to the surface at sea level, it's about 1,000. And then we have altitude. So as you go up in the atmosphere, what you should notice is that the pressure decreases. It gets lower and lower and lower. So what I want you to do is basically just observe what pattern you see in the graph of the atmospheric pressure. And then based on that, which of the following images, A, B, C, or D, best represents the distribution of oxygen and nitrogen in Earth's atmosphere? So at the top of each graph here, basically this would be at the thermosphere, top of the atmosphere, and then you'd be at the surface if you were down at the bottom of each image. So now that we understand pressure, air pressure is just the pressure you feel, the weight of the full atmosphere pushing down on a given point. We can also define density. So we already know what density is. Things that are less dense, they tend to rise. Things that are more dense, they tend to sink. So warm air versus cool air, they behave very differently and they are what drive weather patterns. So if you understand how air behaves in response to density, you can understand weather systems. So this diagram that I have here on this slide is pretty important in terms of understanding weather for the next set of lectures. And I'll recap it again. But let's say, for example, that you have a cube of air. So inside of this cube of air, you have red corresponds to nitrogen molecules, and then blue corresponds to oxygen molecules. Let's say you heat up that cube of air. So you're starting with this cube here. You heat it up. So by heating something up, you are increasing the volume. Heat makes things get more excited chemically. So if you have things that are more excited, they're moving, they're vibrating around more, they're going to spread out a little bit. So the volume increases, and this becomes less dense because if density is mass divided by volume, by increasing volume, you have made this less dense. And you can see that visually here that these molecules in the middle, our original cube, are more close together. They're packed more tightly. Now that they have spread out, they're less dense because there's more space in between them. So Volume increases are associated with warm air and rising air. If you have a lower density, less dense air is going to rise because of its lower density. So, warm air, rising air has a high volume and it is less dense. The other thing about air pressure is that we call this under low pressure. So if something is a low density, it's under low pressure because there's not a lot of forces that are squeezing those molecules back together into a tighter cube. Hopefully, this makes sense. So low pressure, warm air, rising air, less dense air, those are all the same thing. If we go the opposite way, just so I can finish up these definitions here. So say you take your same cube and then you cool it down. So if you take your same cube of air and you cool it down, what's going to happen is that the molecules are going to get closer together. So you're going to have a smaller cube. It's going to be packed into a smaller area. So now it is more dense. Your molecules that were farther apart are now squeezed close together. So you have more mass per volume. So you have a higher density. So cool air or cold air is dense air. And cold air sinks because it is more dense. So if you have high density air, automatically you can assume, you can make some assumptions about it, that it's going to be cool air, it's going to be sinking air, and it's under what we call high pressure. The reason it's under what we call high pressure is that you have these forces that are pushing those molecules closer together. And because it's more compact, it's under more pressure as those molecules are close together. Okay, so your final quiz question here for this lecture. In a few sentences, I want you to summarize the relationship among density, temperature, and pressure in a mass of air. So basically, you're just going to put this into your own words, what I just described. If you take that cube, heat it up, what happens? Take that cube, cool it down, what happens to air?